Now that we have seen isomorphism in detail in the previous session, let's look at Cayley's theorem. It says every finite group is isomorphic to subgroup of a permutation group. So let's see. Given a group G under an operation star, it is closed under the group operation. That means A times B is in G, where A and B are also in G. Now, taking the product of an element with the group elements, including itself, it results in a permutation of the group elements on a bijective basis. Yes? So that basically means that every finite group is isomorphic to a subgroup of the permutation group S sub order of G. Let's understand this a little bit clearly using an example. So let's take S3 and its Cayley table. So taking the product of an element with the group elements, including itself, gives us what? It gives us each row of the Cayley table, isn't it? We take 12 and take the product with the group elements, which gives us the elements of the row. And each of these rows are nothing but permutations of the header row. Okay. So for each G in G, L sub G is a mapping from G to G, where LG or L sub G of X is equal to G times X. So here G is in G. So we are taking one specific element of the group, say 12, and we are multiplying it with all the elements of the group. This mapping is bijective, 1 to 1 and on to. For example, if G, we take it as permutation 1 to, then LG sub 1 of X, that is of 12, is equal to, so 12 times E is 12, 12 times 12 is E, and so on, which is just a permutation of the header row in a Cayley table. Similarly, multiplying 13 with all the elements of the group gives us another permutation of the header row. So every element multiplied by all the elements of G produces a permutation of G. The collection of these rows is a set of permutations of G. So these permutations form a subgroup of the symmetric group S sub order of G. So here, what does that mean? It is symmetric group S sub 6, because order of G is 6, because there are 6 elements. And we can check for closure. L sub G1 composed with L sub G2 of X is equal to G1 times G2 times X is equal to G1 times G2 times X is equal to L G1 times G2 of X. So this we can write it as pi maps G to S sub order of G, where G maps to L sub G. And this pi is a group homomorphism. So it is not a isomorphism. This is a group homomorphism. Now, so where does this isomorphism fit in the picture? Remember, this maps to a subgroup of S sub order of G. That means it maps to a subgroup of S6. So that means we are having an isomorphism between S3 and a subgroup of S6. So in case of S3, we have S3 is isomorphic to pi of S3, which is a subgroup of S6. where pi maps S3 to S6. But remember, S6 has 720 elements, whereas S3 has only 6 elements. So this is not going to be onto. There will be lots and lots of elements in S6, which will not be mapped from S3. So that is why we are saying that pi of S sub 3 is a subgroup of S6. Okay, now here we have used pi, differently in two different contexts. So in quotient groups, pi maps G to G by n, where an element of the group G maps to the coset G times n. Here pi is called the canonical projection or quotient map, since it projects each element of G onto its coset in the quotient group G by n. Whereas in Cayley's theorem, we are saying pi maps G to the symmetric group S sub order of G, where G maps to L sub G, is a group homomorphism embedding G into the symmetric or the permutation group of its own elements. Here pi is called left regular representation or an embedding or a Cayley map. That is Cayley's theorem. Every finite group is isomorphic to a subgroup of a permutation group. So that was Cayley's theorem. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.